Morning, good afternoon, and good evening, depending where you are. Welcome to the 8th JMD Webinar series. And I would like to introduce three organizers of this webinar. Professor Leila Notash from Queen's University in Canada. She's also an associate editor of JMD. And Professor Girish Krishnan from University of Illinois, Urbana-Champaign. He's also an associate editor, as well as Professor Faez Ahmed from M.I.T. And he is a features article editor, as well as a webinar extraordinaire. So we are very grateful for their time to, organize this, to, select the papers and, communicate with you for the webinar. Last but not the least, I would also like to thank Amy Susky, who is an assistant to the editor. And, Amy is really the one who make the JMD Journal the world terms. Without further ado, let's begin.
Okay. Thank you, Jeff. So in addition to thanking my co-organizers, we would also like to thank Jeff as the editor of Mechanisms for his support throughout organizations of this webinar, and Amy's support as well for the event, as well as the support of the editor-in-chief of the Journal of Mechanical Design, Professor Sipersad. As you may know, these webinars are generally organized quarterly by the Journal of Mechanical Design's editorial board in order to feature the research work published in the recent issues of JMD, as well as to connect the engineering design research community. Each webinar has two sessions. The first part is the Zoom that we are just started, and it includes the presentations of the papers as well as questions and answers. Following the Zoom session, we will gather for about 30 minutes using GatherTon, and you will have access to the URL for that in the chat. And it will be used for further discussion and networking among the speakers and the attendees. Girish, would you like to say a few words regarding the theme of today's webinar?
Sure. So the theme of today's webinar is co-design of robotic systems. So as we all know, traditionally robot design is done sequentially. So we first have the hardware, and then we retrofit the actuators, and then the control system is formulated, and that makes the entire system work. But this is found to be not so optimal. And in future, robots are going to be designed by considering actuation, controls, and the hardware all in a single loop. So this is the feature of co-design, as it may lead to a lower power consumption, better optimality in terms of combined design and controls in terms of the system itself. And to that nature, most of the papers that are going to be presented today have some form of integration of actuation or controls, or even the entire system within their design framework. And we are very eager and interested to hear from our four speakers on how all these various systems, or all these various subsystems, integrate within robotics design. Thank you.
Thank you, Girish. So we have four presentations, and these are based on the papers published in the 2022 and 2023 issues of JMD. The first presentation is on the novel design of a rotation center auto-matched ankle rehabilitation exoskeleton. Sorry, I can't see my own screen. With decoupled control capacity. And it will be presented by Dr. Tan Wang. Dr. Wang received his BSc and MSc from China and his PhD from King's College London. In fact, he just completed his PhD very recently. So congratulations, Dr. Wang.
Thank you, Professor.
You're welcome. His research interests include rehabilitation robots, reconfigurable mechanisms, multi-finger dexterous robotic hands.
Okay, thank you for the introduction of my background, Professor Leila. Then I will introduce my work. So first I will share my screen. Hello everyone. My name is Tun Wang, and I'm very glad to share our work with you. The paper title of our work is Novel Design of a Rotation Center Automatic Ankle Rehabilitation Exoskeleton with Decoupled Control Capacity. Here is the outline of the presentation. First, it is about the state of the problem. Stroke remains the second leading cause of death and the third leading cause of disability in the worldwide scale. Stroke survivors frequently suffer with hemiparesis or partial paralysis, which considerably constrain motor functions of patients' lower limbs. Compared to the traditional manual therapy, the robotic solutions show great advantages in assisting patients' rehabilitation and activities of daily living. In addition, ankle-foot complex plays a vital role in supporting body weight, maintaining balance, and providing propulsion. Its dysfunction is a common and persistent symptom. Therefore, our work focuses on the design of ankle rehabilitation exoskeleton. In terms of structure features, ankle rehabilitation robotic systems can be grouped into ND fighter and wearable systems, and the former can be further divided as PR and FR, and the latter can be reclassified as EXO and AO. These mechanisms are developed for different rehabilitation phases, which mainly include preliminary or early, intermediate, and advanced functional rehabilitation stage, as shown in this slide. In the initial phase, passive and active exercise are needed to promote patients to restore the ROM and strengthen the weakened muscle. The proprioception or the intermediate exercises initiate after the patients achieve a certain weight support capacity and aim to help them recover balance and posture control. The two stages share a common feature that they can be completed where patients are resting in a fixed position, which do not entail locomotion. Therefore, the two phases can be defined as a stationary rehabilitation stage. Comparatively, the advanced stage focuses on maintaining balance by controlling the ankle tugs during walking and assisting patients gradually regain and improve independent walking abilities. Hence, this stage can be defined as dynamic rehabilitation stage. Our initial target is to design a reconfigurable ankle rehabilitation device that can provide both stationary and dynamic rehabilitation exercises. We have published that design details in this paper. And today, the paper I will introduce is mainly about an analysis on dynamic rehabilitation configuration of this reconfigurable design. In designing such an ankle rehabilitation device, the mechanism center is required to match that of ankle-foot complex, since the misalignment may lead to discomfort, pain, or even secondary injury to the biological joint. Conventionally, in existing designs, the ankle-foot complex is usually reduced as a two-axis rotation model or a 3-axis rotation model. The 2-axis rotation model is adapted from the skeletal structure of the ankle foot complex and comprises 2 serial revolution joints. However, because of the individual difference, it is not possible to provide a unified 2-axis rotation model. In comparison, the 3-axis model is proposed based on motion features of the ankle foot complex. It is virtually a spherical joint and can describe 3 rotations of the ankle, which are DP, IE, DP, IE, and AA. It is also the model I import in the design. This slide shows the architecture of the design. Apart from the brace, the foot plate, it comprises 2 drive links, L1 and L2, which respectively have a UPO and SPO configuration. In the basic geometry, AI here represents the connection points of the brace and the actuators. The lower connection points of the 2 actuator links to the foot plates are marked BI. Point O here represents the ankle foot complex. Then, for an arbitrary configuration of the mechanism, we can derive constraint screw systems of link L1 and L3. Where reciprocal calculations, we can further get the foot plates motion screws. Then the motion features of the mechanism can be summarized. Firstly, the mechanism's rotation axis passes through the complex center. Secondly, impulses where U11 and U21 here. This is U11 and here is a U21. When the 2 axes have an intersection, we can determine 2 rotation axes, A1 and A2. As shown in this figure, A1 is coincident with the line CO, and A2 is a normal of plane A1, B1, PG. In another case, when U11 and U21 are parallel, A1 will turn into X1. In addition, we can conclude that any line that's in plane pi 4 determined by A1 and A2 is a rotation x of this mechanism. Then, based on the analysis above, we can determine the rotation matrix of the mechanism. In this expression, alpha and beta respectively represent the rotation angle about x1 and xa2. In the expression, Olen alpha apostrophe here is the unknown quantity, which can be further determined from the front wheel of the mechanism. As shown in these figures, 2 different cases can be classified. In case 1, BI are not at the same height as O, and in case 2, BI are at the same height as O. After analysis, we can get the specific expression of alpha apostrophe in different cases. This formula shows the specific expressions. After we determined the rotation matrix, then we can, in addition, the rotation of the foot plate can also be described by Euler angles about axis of the global frame, which are denoted by alpha 0, beta 0, and gamma 0. These 3 angles also indicate the IE, DP, and AA motions respectively. Then we can find the relations between alpha, beta, and alpha 0, beta 0, and gamma 0. The specific relations are displayed here. Further, we can find that In case 1, if alpha and beta are non-zeros, the mechanism will generate a compound AA motion, which means that gamma 0 in these cases will not be 0. Also, the larger the value of H1, the larger the maximum value of gamma 0. As a comparison, case 2 will not generate the composed AA motion, no matter how alpha and beta change. And in this case, alpha equal to alpha 0, beta equals to beta 0. Existing investigations show that AA motion has marginal contributions to the gate rehabilitation, although the maximum values of gamma 0 in case 1 are not large. So case 2 is more suitable for dynamic rehabilitation. Therefore, the following analysis will focus on case 2 to fully illustrate its superior performance in other aspects. First is about the kinematics analysis. The inverse kinematics aims to compute the input values required to drive the linear actuators when the foot plate's orientation is determined, and forward kinematics is the reverse process. These figures here validates the inverse and forward kinematics solvers. In addition, via kinematics analysis, we can also find that the mechanism has a decoupled control capacity. From this animation, we can see this feature. The IE motion can be here can be individually controlled by it should be L2 here. This link is L2. The IE motion is individually controlled by L2. And here for individual DP motion, it can be individually controlled by L1 link. So this animation shows its decoupled control capacity. The singularity of the mechanism is investigated by computing the determinant of Jacobi matrix. As indicated in this figure, singular positions represented by curves labeled with O or 0 are located at the periphery of the specified computation range. Further, this figure displays the exoskeleton's theoretical workspace, which is indicated by the irregular green area. It completely covers the prescribed realm that represented by the right rectangle. The next stage, we analyze the dexterity of the exoskeleton. In the first formula, sigma mean and sigma mix are respectively the minimum and maximum singular values of the Jacobian matrix. Therefore, LDI lies in the range from 0 to 1. The higher the value, the greater the dexterity that the mechanism will exhibit. And GDI is defined by the second formula, which is able to describe the overall dexterity level in the target workspace. From this figure, we can find that the discussed case displays a good dexterity in the prescribed workspace. Then we evaluated the actuation requirements. First, it is about the actuation force, which can be calculated via this equation. In the calculations, to obtain a conservative estimate, extreme cases are considered, where the ankle toes are most consistently kept as boundary values. Then the actuation velocity can be evaluated by this equation. Based on aforementioned analysis, it is possible to find suitable commercial actuators that can be potentially used to construct the exoskeleton. The exoskeleton's adaptability is investigated subsequently. For patients with smaller heads, small size actuators are needed for ensuring the wearing safety and the comfortableness. The left figures shown in this slide demonstrate that the design is still able to achieve the prescribed realm after reducing actuator stroke length, although the achievable workspace shrinks. Besides, we investigated the influence of the actuator's screw's maximum retractable distance on the device's performances. As shown in the right figures, it turns out that the shorter the stroke, the smaller the adjustable range of the retractable distance. But the range can be improved by decreasing the geometrical parameter Ri. Then is the conclusions about this paper. First, the proposed novel rehabilitation exoskeleton has a UPU and SPU architecture, which is capable of automatically matching its own rotation center with that of the ankle foot complex when it is worn. Secondly, the two-dolphin mechanism can provide two rotation patterns. Case 1 is able to provide a copped AA motion, while case 2 only preserves two primary motions during dynamic exercises, which are IE and DP. Thirdly, the singularity loci are far away from the exoskeleton reachable workspace, which completely incompresses the prescribed ROMs. Last but not least, the 90-degree arrangement case of the mechanism can realize decopped motion control and display a good dexterity performance. Then further analysis on actuator requirements and applicational adaptability show that the proposed design is manufacturable and suitable for patients of a wide range of heights and weights. Okay, this is the end of my presentation. Thank you.
Leila, you're muted.
Thank you, Girish. Thank you, Dr. Wang. We will have the question and answers. It was a very interesting presentation and work. We will have the question and answer period at the end after all four presentations. So I will quickly share my screen.
Okay.
So next presentation is on the reconfigurable robotic system design with application to cleaning and maintenance, and it will be presented by Dr. Amir Hayat. Dr. Hayat is a research fellow at Engineering Product Development at Singapore University of Technology and Design. He's currently leading the design teams on deployable reconfigurable robots project. Dr. Hayat received his PhD from M.I.T. Delhi in India, and he has over 35 scientific papers, 3 design patents, and he is the lead author of the book entitled Vision-Based Identification and Force Control of Industrial Robots. Okay, Dr. Hayat, you have the floor.
Thank you. Thank you so much for the introduction. I'll just switch on to the full presentation mode. Just to check the screen is visible to all?
Yes.
Okay, thank you so much. So good evening, good afternoon to all of the participants and those who are joining in the online mode. Today, again, thank you ASME for providing us the opportunity to present our paper. So today the paper which was selected at ASME is Reconfigurable Robotic System Design with Application to Cleaning and Maintenance. Myself, Abdullah Mirhat, and my co-authors are Limi Manivan Kalimatu, Professor Mohan Rajeshidara, and Professor Chris L. Wood. So this is the paper accepted, and we start with reconfigurable robots. So the popular perception of reconfigurable robots are generally coming from the Transformer movies, and as well as the toys that are reconfigurable in nature that can change its shape and perform multifunctional locomotion and functionality at the same time. Moving further, in the domain of robotics, it is giving active research attention, be it the application of accessing narrow passages. Then initially the reconfigurable robot design was more focused on the mechanism development and control. Now it's more also focused on application, looking at the reconfigurable drones and as well as the floating water robots that are also reconfigurable in nature. Our group at SUTD mainly focuses at developing applications centered around cleaning and maintenance. So these are some of the robots that were developed in our ROAR lab under the guidance of Prof. Mohan. So this is H-Tetro, which can change its shape into 7 forms. These are staircase climbing robot, referred as the Tetro. These are again for vertical glass facade cleaning, which can traverse over positive obstacle that are aluminum glass panels. Then this is a Scorpio, which has a capability to crawl, roll, and climb wall as well. And these are some medical mobile-based robots which are capable of joining and connecting and disconnecting, is also like nested reconfiguration. And today, our focus will mostly be on the development of this reconfigurable robot, which we did for payment sweeping task. And this is a system which is aimed at sweeping, but it also contains several subsystems. Reconfigurable robot, in summary, can be referred as having an ability of multi-ability, like it has an evolution and survivability. And it possesses an ability to autonomously change the shape and adapt optimally to the specific task or environment. In one of our work, we have defined and classified or taxonomy of these robots are represented, where the intra, inter, and nested reconfigurability concept is presented. So intra is one robot can change its shape. Intra is one robot where it can change its shape into several forms. Then inter is 2 or more robots combining together. Then nested is a combination of both, where the advantage of both the worlds are taken. So 2 intra-robot joining together results in a nested reconfiguration. So this paper can be referred to this link. Moving on the next aspect, the design approach. So typically it is inspired from 4D double diamond, that is discover, define, develop, and deliver. But is in context of reconfigurable robot, our group is actively involved in designing several of these architectures. The process which involves is like being presented in a heuristic way that starts with looking at the environmental conditions, the requirements, and then we structured it into 3 layers, that is input layer, then formulation layer, and then the output layer. I'll be defining more in context of the development of this robot and how this forward design and inverse design aspects are taken as the speaker. Introducing the aspect of like designing robots starts from actuators, and what is nowadays more of like coherent approach of designing is taking place. So typically, we can also do first the analysis and simulation, and then can develop the robot, or we first develop the robot and develop the formulation layer. So vice versa, it results in forward and inverse design. So the first layer, as it talks about the input layer, that is generally concerned with the environmental requirements and the process and sequence of application that will be required. And today my talk is mostly focused on designing of a payment sweeping robot. So we looked at different condition of payments that exist specifically in Singapore context. So we can see that there are wide payments, sharp turns with some bumps, then irregular surface as well. There are sharp changes and corners, and the objective of these robots are to enhance the area coverage task. So looking at this, we laid down the requirements and environmental conditions. Then based on this, we set the process sequence for our design of robot, and which we start with like proof of concept in the form of animation, which states that the robot should behave like to adjust itself in a different pavement width, and also it will allow the commuters or the pedestrians to move in a VR where it can shrink and allow the pedestrian without hindrance. Moving on further, talking about the heuristic approach we take. So first we gather a detailed information in the input layer, what is the requirement, and as shown in the animation, we decided to have a robotic system which can expand and collapse. So we look at the behavior layer, which is mostly like as an output, we can observe it. And a detailed work of the transformation design principles were presented long back in 2009 by a researcher. And then it is a fundamental work which looks at suggesting the design principles and facilitators. We adapted that work in context of designing reconfigurable robot, how it can be used efficiently to design these reconfigurable systems. So in that work, the authors proposed the principles and facilitators. We tried to map it with the reconfigurable robotic system. So what are these? Just to show it with animation, is expand and the principle. It consists of 3 principles, that is expand, collapse, expose, cover, and fuse and divide, which are shown with the help of animation, which is again taken from the Google animation source. Yeah, so these are like by and large the principles which are suggested in this work. And then moving further, there are facilitators which assist in achieving these principles. So altogether, 20 facilitators are listed. And basically this work it can be seen as like a trail which helps in designers to aggregate. Similarly, this facilitators and principles are generic in nature. It can be applied to the products as well as the reconfigurable robots. So our study mainly focused on the reconfigurable robots that can be done using these principles and facilitators. Looking at these are some of the examples which shows like generic connections, fold, material flexibility, and nesting. There are altogether 20 facilitators listed. And how it can be used, we have illustrated in our work, so which focuses on design of reconfigurable systems and subsystems. So for designing a typical pavement sweeper, it consists of, say, transmission, that is a locomotion unit. It should have a varying footprint, then outer cover, storage bin, surface cleaning mechanism, and vacuum suction blowing unit. These are by and large the subsystems which are required for any typical sweeper robot. So we expanded on this, like what, say, transmission, because it is again needs to be expand and collapse. So it needs these are the requirements listed, and then the corresponding principle and facilitators that can that assisted in designing these systems are listed here in form of, say, P1, then fold, modularity, function sharing, and shared power transmission. How it looks is basically these are the steering units which also assist in locomotion. So it's a differential drive. Each unit is a differential drive locomotion unit, which helps in steering as well as locomotion. So then moving on further, we conceptualize to have a varying footprint, and then the principle involved is like again expand and collapse. The facilitators that help us in designing this are fold, function sharing, and shared power and transmission. With the help of video, one can see that these lead screws are used in support with these steering wheels. So once it will shrink, it will be assisted by the force transmitted through these wheels in the direction while it is reconfiguring. So it's a right-handed lead screw and left-handed lead screw. Just a single degree of freedom resulting in expand and collapse here. So it's also being highlighted as a shared power transmission because multiple steering units are being used to gain this expand and collapse once the system will be grounded, which I'll be highlighting in the coming slides. Then it requires an outer cover, which also needs to complement the principles, that is expand and collapse. So again, the principle involved for this design should be expand and collapse. What the facilitators we have selected are fold, function sharing, material flexibility, and enclosure, because these are the requirements, lightweight, flexibility. So those keywords resulted in selecting these facilitators. And as you can see, we use something similar to a bellow mechanism for this expand collapse feature for the cover. Similarly, the sweeping brush is an essential subsystem which is required for the surface cleaning. These are the requirements listed, and the principle again is expand and collapse, and also the facilitator is modularity and conform with the structure interface, because the sweeping unit should attach itself to the surface while cleaning. So we can also adjust the force required for the sweeper while cleaning a given surface. So this is a subsystem of this cleaning and maintenance robot named Panther. Similarly, we looked at other two units which are at concept stage. So this is more like a blower and suction unit with the same mechanism, and also the storage bin, which should complement the expand and collapse feature. So it also is based on the principle expand and collapse, with the facilitators involved are fold, function sharing, and material flexibility. Moving on further, so we looked at the behavior aspects which are derived from the requirements and how it resulted in selecting a certain mechanism to achieve that. So now we look at also the mechanism layer. So principally for this expand and collapse, this mechanism was used, and for the first time it was presented in a conference icon. Because we are interested in also looking at the mechanism layer, so just slightly deviating from the presentation, one outcome of this research that we started around 2018-19 that resulted us in also structuring it in more formal way, that how a designer can think and assist using mechanisms. So we have one of the work I presented in IDETC, which lists down these facilitators supporting with the mechanism. So it will help mechanical engineers who are like freshmores and whether they are skilled or novice, or so that will help them to ideate and what mechanism can support these behavior, mainly expand, collapse, fuse, divide, and expose and cover. So this work can also be referred to. Coming back to our work, with the development, we also look at the shapes and different gates, because reconfigurable robots have their interesting features that they can provide us with different gates which are according to the requirements and which are which results in different functionality. So this robot can also like do static reconfiguration by keeping at its space. It consists of 3 frames, so one of the frame can move left and right. So it results in like shrinking in one side, then shrinking along the middle frame, and then shrinking along the right frame. Similarly, one interesting feature that we have experimentally shown and published in some of the works that proves that how the reconfiguration while locomotion is attained, and is also highlighted in this paper that today we are presenting. So coming on to the video, because now we have mostly talked about the robot in terms of say images. So as a proof of concept, we start with the animation. Then we looked at different subsystems which will support this requirement or the behavioral requirement at that for this robot. So this is like a mechanism analysis, the simple single degree of freedom mechanism. And these are subsystems like more at locomotion level, electrical units, and safety and control that goes into this building of this robot. Moving on further, as this framework is just the main one of the main aspect that is proposed in our work. So now we, after development of this robot, we also look at the functions that basically deals with kinematics, dynamics, control, and mobility. So for control, we suggested a cascaded controller for each of the steering mechanism, and because it's uniquely like it's a mechanism which is supported by 4 independent steering drive. So it results in like 0 turning radius, or it can attain any arbitrary instantaneous center of rotation, except the axis of these steering unit, because that will result in singularity. So moving on to showcase again with the help of this video, we have tested this ability of locomotion unit. This is referred as locomotion while reconfiguring while locomotion. So one of the frame is moving along the straight line, and then this is moving towards it. Similarly, the center, it will move along the center line, and then both the frames will converge towards its central frame. So these are the modes of reconfiguration that are proven experimentally, and some of the tests in the outdoor settings to test the control that we have suggested in the paper. Some other nice applications can be developed, like detecting the human density, and accordingly it can adjust. So these again are the proof of concept that were done during the initial development phase of this robot. Moving on again further block by block, starting with input layer, then output, then formulation layer. In formulation layer, we have done the kinematics, dynamics, and kinematics and controls. We looked at the mobility, even done the dimensional synthesis. For more like model-based control, we are also we also propose some of the work which looks at the dynamics of this robot as well. Then we performed, once the system is up, we've done several subsystem layer testing under failure mode analysis, failure mode and effect analysis, and these are listed in the tabular format in the paper. One can go into the details by looking at it. So majorly we look at these 5 subsystems, which are the subsystems involved with this robot. Another outcome of this work is we detail it in the form of another design work, that is iteration in design and development, where we looked at also the taxonomy. We defined that how iteration is carried out at a different phase for a given project that we have the help of our funding agency. Then these are the 3 versions. Currently, we are working on the current version of this for the autonomy test. So for the failure mode effect analysis, these are several, some of the conditions that were used to test it under, say, varying the inclination angle, moving on the fixed inclination angle in our campuses, then different surface conditions, like soft surface, then like wooden surface. Typically, over here, the grass are not wet. So in case of wet condition, that we observe the sinking of this wheel, then we decided to increase the diameter as well. Then the advantage is it can fit to even the lift, loading lift that we have. It can shrink and then take a lift, and then we have tested it in the night conditions. So these are several tests which were planned, and it has also a capability once the robot, the motors got some problems or limitations, then it can also be pushed by a single person. And these are some of the locomotion capability moving sideways, which will enhance the area coverage. So with this, I would like to conclude my presentation that our work uniquely looked at designing a reconfigurable system, evolving the fundamental transformation principles that are expand, collapse, use, divide, and expose and cover. We looked at the attributes of designing the reconfigurable robots, illustrated with the functional design of the proposed robot, and then the framework is more generic in nature. It can be scaled for other reconfigurable robot design, or in general also robot development. Future work aims at expanding our scope of transformation principle in context of other robots as well, and we are actively looking for the design science publications and considering ASME as one of our venues. Again, we like to acknowledge for our work our funding agency, that is National Robotics Program Singapore, and Singapore University of Technology and Design, and our co-authors, Limi, PhD student, Manivan and Kalimuth, who is also a PhD student, Prof. Mohan Shilana, and Prof. Tesud. Again, I'd like to thank you, ASME, for providing us this opportunity to share our work with the community. In the end is one of the book that during the introduction was highlighted. So I take this opportunity to highlight this outcome as well. So this is not focused around the development of this reconfigurable robot, but it's more of the work that was carried out during my PhD time. And I would also like to invite the audience of today's presentation to go through this SMORPhy, which is education robot, a STEM-based learning education robot, which is based on the theme transforming learning with transformer robots, or the reconfigurable robots. So we are having this first round of our workshop being carried out this month, and this event will continue. So one can check the website of VIFA Robotics. So with this, I come to an end to my presentation. The question and comments, I will be happy to get the comments and questions in the given slotted time. Thank you so much.
Thank you, Amir, for an excellent, exceedingly interesting presentation. Of course, the questions will be at the end. So let's move on to the next speaker. Amir, if you can stop sharing your screen. Let's see. So the third presentation is from Cecilia Skokcia. Cecilia, please correct me if I'm mispronouncing your name. So she has...
Yeah, it's correct. Skokcia, if you see me.
All right. So she has a master's degree in mechanical engineering from Polytechnic University of Marki Italy, in 2019. She is currently a PhD student and research fellow in the Department of Industrial Engineering and Mathematical Sciences in the Polytechnical University of Marseille. Her research interests include cooperative robotics and mechatronics. So with that, Cecilia, your paper is Design of a Tensegrity Servo-Actuated Structure for Civil Applications. The floor is yours.
Thanks for the introduction. Okay, so can you see my screen?
Not yet.
No? Can you use now?
I cannot see it, but
no, I cannot see it too.
Okay.
Okay. I'll try again. Okay, now?
Yes, it's beginning. Yes, yes, now I can. Yes.
Right.
Okay. Okay, so
Perfect.
thanks for the introduction. I'm Cecilia Scoccia and I come from the Polytechnic University of Marche in Italy. And today I'm here to present the paper called Multibody Analysis of the Integral Servo-Actuated Structure for Civil Application. So first of all, the term tensegrity derived from the contraction of the term tensional and integrity, and it was coined by Richard Bach in 1940. This terminology implies the integrity of a structure in equilibrium with continuous structural elements in tension that are the cable, and the discontinuous compressed elements, the struts. The tensegrity structure are simple and efficient from an engineering point of view, and they maintain the functionality with only the smallest possible number of structural components. According to René Metro, these are systems in a stable self-set state, and they include a discontinuous set of compressed components inside the continuum of tensional components. So first, the outline of the presentation will be an introduction to the tensegrity floor. Then we move to the multibody model and the proposal for the mechatronic system. And then we will have a look to the simulation and the experimental result. The tensegrity floor object of this study is an hybrid glass metallic structure characterized by a lightweight metallic subframe sustaining a glass floor decking. Thanks to its transparency, the floor fits those applications where a low impact is required. For example, in the case of coverage of archaeological sites. The main novelty is the introduction of the glass plate as structural elements. Thanks to the design additive joint, the glass is no longer in the simply supported configuration, but it guarantees an actual contribution towards the reduction of the deformation of the system. At the base of the effectiveness of the tensegral structure, there is the correct tensioning of the metal frame, which purpose is to keep the rigid element compressed. The tensioning level is the responsible of the actual deformation of the structure. Since this kind of structure is subject to significant deformation, a mechatronic servo system is proposed aimed to maintain correctly the stress of the metal cables. The floor is realized by two different levels, and a set of strands is used to connect the upper and the lower level of the structure. A series of rigid beams, which are axially compressed, are diagonally disposed between the upper and the lower level of the structure. Tensegrity structure are affected by a large displacement depending on the internal stress of the strands due to the kinematic of the system. In order to investigate the behavior of the floor, the structure is modeled in a multibody environment. So an hybrid rigid elastic approach is used. In particular, we with the exception of the metal cables, so the upper, the lower, and the lateral strands, all the bodies are considered rigid. The connection among the cubes and the strands are allowed by the holes on the face of the cubes, through which the cable are inserted. Thanks to this connection, each cube can both rotate around and translate along the axis of the cable, realizing through a cylindrical joint. The glass tiles in the upper surface are connected to the subframe by adhesive joint. In particular, each glass is connected to 4 different cubes by means adhesive joints, realized with structure epoxy resin. The multibody object is modeled as an equivalent set of concentrated 6 degrees of freedom elastic elements. And a finite element analysis was used to determine the stiffness of the adhesive joint. Since this kind of structure is subject to significant deformation, based on the result obtained by simulation, a mechatronic system for the servo actuation of the structure is proposed. And the principle is to vary the tension of the cable to vanish the decking deformation, measuring the vertical inflection. So in this case, lateral cables are chosen thanks to their easy access for the implementation of the electric actuators. A possible solution is providing each couple of lateral strands with a linear actuator able to modify the internal stress. So a standard proportional derivative control loop which regulates the tension based on the measurement displacement can be implemented also in simulation in order to optimize the control strategy. So 3 different feedback control schemes of different complexity are investigated in terms of the response to the application on a static load to the upper surface. In the first control scheme, the lateral cables are actuated based on the deformation, and in this case, the more complex in terms of actuation. In the second, all the actuators are controlled by means of all the central node translation. And the third one is a simplified actuation with a reduced number of actuators, so only 1 actuator per edge. These 3 control schemes have been tested in simulation environment to observe the response of the structure when we apply an external load to the upper surface of the glass decking. Without control the lateral strands, the initial strain of the lower cables move upwards the glass surface. So the better solution is provided by the control scheme 1, which is able to vanish the vertical displacement of all nodes, and a complete compensation on the floor is obtained. In the case of control scheme 2, only the central node recovers the deformation, but at this point it's more convenient to use the control scheme 3 with a simplified solution. The real tests on the tensegrity floor were performed by reproducing the pedestrian load condition. The static load was applied according to the values provided by the Italian technical standard, and the 3 loading conditions are the symmetric load distributed on the central span, the asymmetrical load distributed on the lateral span, and the uniformly distributed load. So each load configuration was applied both in the case of glass panels simply supported on the metal substructure and the panels bounded to the substructure by adhesive joint. And also 2 different measurement systems were used and compared in order to measure the displacement. In the first case, we used an optical measurement using 2 different cameras with different angulation, as is possible to see from the figure, and an inductive displacement transducer measurement using PT50T sensors. The result obtained with the different load combination are reported. So the measurement displacement for the different constraint configuration are realized. In particular, the first figure, this figure shows the graphic mapping of the vertical displacement values recorded by both the optical and digital measurement for the structural configuration with simply supported deck configuration. But in this case, in the first case, the deflection exceeded the maximum allowable value indicated in the Italian building code. The second figure is about the use of a different kind of adhesive, and also in these two other figures, it are reported the mapping of another kind of adhesive and with the use of silicone. The result of these different measurements show the elastic behavior of the resulting hybrid system. And the results show the effectiveness of the adhesive technology in increasing the overall stiffness of the structural elements compared to a simply supported configuration. So the choice of the adhesive is determined not only by the cost, but also thanks to the mechanical properties. At the end, we choose the adhesive too, because nevertheless, the epoxy resin 1 offer better performance, but it's more expensive and has a lower glass transition temperature. So in conclusion, in this work we presented a novel glass floor based on tensegrity principle for a civil engineering application with low weight and low visual impact. We also obtain acceptable deformation maintained by actuation of metal cables. We also model the entire system using an hybrid multibody approach, and we also proposed a minimal actuation scheme, keeping acceptable values for the system. And in the end, also the use of structural adhesive allow a significant increase in stiffness under different conditions of load. So thank you for your attention.
Thank you, Cecilia. A very interesting presentation. So if you can unshare your screen, let me just go back to my... Okay. So the fourth presentation in this webinar is going to be from Hongyang Tang. So Hongyan is an assistant professor in the Institute of Rehabilitative Engineering and Technology, University of Shanghai, Science and Technology in China. He obtained his MSc from Beijing Jiaotong University, China in 2012, and a PhD from the same place in 2019. His interests include parallel mechanisms, robots, rehabilitation robots, and control applications. So Hongyan, you may begin sharing your slides.
Okay. Okay, can you see the PowerPoint?
Yes.
Okay. Hi, everyone. I'm Hongyan Tang, and I'm from University of Shanghai for Science and Technology. Today, I'm here to introduce our latest research and two-wheeled self-balancing robots. So the paper title is the optimum design for a new reconfigurable two-wheeled self-balancing robot based on the virtual equivalent parallel mechanism. And today, we are focused on these three questions. The first one is why. Why are we doing this research? Our research object is the two-wheeled self-balancing robot. Now, the two-wheeled self-balancing vehicle is already very common. So why do we need to continue researching it? As we all know, the two-wheeled self-balancing vehicle is a dynamic balance system. Therefore, the balance condition of the robot has a range. When the robot's angle is greater than a certain threshold, the robot cannot return to the balance, and the robot will fall down. We are wondering if it is possible to make a fallen robot stand up by itself. Okay, let's see. Let's take a look at this video. Okay. Okay, obviously the robot cannot stand up by itself. So at the same time, we are also wondering if the robot can climb the stairs by itself. And let's see the next video. Okay. Okay, this video cannot work. Okay. But the robot cannot it also failed to go upstairs. And we're also wondering if the robot can cross the obstacles. Okay. Why it doesn't work? Okay. Sorry. Okay. Okay, the robot without the configurable mechanism also failed to cross the obstacles. Okay. Next, I will explain. Then I will explain how we solve this problem. At first, we analyze the reason why the robot not stand by itself, which is that the robot's moment of inertia is too large, and the driving force of the robot is not enough to make it stand up. So we want to reduce the robot's moment of the inertia, and we designed a configurable mechanism that allows the robot to switch back and forth between the high moment of inertia and the low moment of inertia. So considering that when the robot deploys, a large amount of energy is required to lift the base of the robot. So we add a spring here, and the spring can reduce the energy required for the base to lift during the deformation. And this is our design plan. And next, how did we implement this plan? In this paper, we built a virtual equivalent parallel mechanism as the mathematical model of the system. And this model is a coupled model that couples the motion of the mechanism and the tearing information. Then we analyze the kinematical and dynamic models of the system. Next, beyond the mathematical model, we discussed the stiffness. We discussed the driving stiffness and the motion force transmission efficiency, and the driving force and the driving power. Next, to determine the dimensional parameters of the mechanism, we used the particle swarm optimization algorithm to optimize the comprehensive performance of the mechanism. And finally, let's look at our research result. The first is the performance comparison of the mechanism. In these four figures, the UN, the red line UN represents the performance of the optimized mechanism, and the blue lines SO represents the performance of the mechanism that was optimized step by step, and the CO presents the performance of the mechanism that was optimized comprehensively. From the result, we can see that the performance of the optimized mechanism is better, and the performance of the CO mechanism is better than the SO. Then we built a prototype and conducted the validation experiments. At the first, let's see this video. At first, we conduct the experiments on driving force and the driving power. from the experiment results, the spring reduced the driving force and the driving power of the mechanism. And this is the okay. Then is the stepwise optimize the mechanism. We can find that after the optimization, the driving power and the driving force of the mechanism were further reduced. And the last one is the comprehensive optimized mechanism, and the driving force and the driving power were further reduced. Okay. And by reconfiguring the moment of inertia, the robot can stand up by itself. And when going up the stairs, okay, it cannot be. Okay, sorry, I will use a lot of. Let's see this one. Okay. When the robot go upstairs, the robot will fall down first, and then climb the stairs, and then with the reconfiguring the mechanism, and the robot will stand up again. Okay. Right. Okay. When the robot cross the obstacles, the robot also fall down first, and then cross the obstacles, and at last the robot will get up by itself. Okay. And finally, at the last, that's the conclusion. The motion experiments verified the great kinematic and dynamic performance of the new two-wheeled self-balancing robot present in our this paper. And that's all. And thank you for watching.
Thank you, Hongyan. This concludes the list of our speakers for today's session. We will soon begin our question and answer session.
Yeah, thank you, Girish, and thank you, the speakers. So we have about 20 minutes for the Q&A, and we will start with the first presentation, and we will allocate about 5 minutes and so on. And at the end, if we have more time, we will come back to the questions of the earlier papers.